Okay, good morning everyone. So I think we should get started. It's 11 o'clock. So we'll have the last lecture on gravitational waves. So please go ahead.
Yeah, so this is the third and last lecture. So let's get started. So what we will try to do today is discuss a bit the difficulties, so all the noise that we are encountering in our measurement, and give you an impression what is limiting our sensitivity. Then we have been running the third observation run that started on the 1st of April, and that we did 6 months of running. We stopped right now to do some commissioning of the instrument, and the 1st of November we start for another 6 months. And then we will stop for 12 months. Oh, sorry, for 20 months. After that, so I will show you what came out of the first 6 months of running, and then we'll talk a bit about the future and see how far we get. So yesterday I talked a lot about the science, and here I give an overview of the main topics. I addressed some of the fundamental physics, like test of general relativity, the echoes, the ring down in spiral merger. There were a couple of things that I didn't talk about, parity violation, axioms. So there are many more physics topics that we could have talked about, dark energy, dark matter. I didn't do much on the astrophysics, a bit about the kilonova, nothing on astronomy, and I told you the possibilities with cosmology. And then the nuclear physics part, where we also now collaborating with people from, for example, Alice, is on the equation of state of neutron stars, because you have 3 times nuclear density. And you can see, if you see phase transitions in there, so we are also looking at that part. So the good news is that this science was recognized, so we got the Nobel in 2017. We should do this more often, it's really fun. And this is Ray Wise. Ray Wise is the person from MIT that worked on the instrumentation. I make the picture a bit bigger because he got 50% of the Nobel Prize. And so this is Kip Thorne, and Kip is the theorist that pushed together with Ray this experiment. And then you see Barry Barish, which many of you know from particle physics. He was also on the SSC. He's well known for the ILC work. And he was the one that set up the LIGO collaboration, also the LIGO scientific collaboration. That was all his work to get it into a well-organized entity. I want to show you these 2 persons over here. So on the left you see Alain Briet from Nice. He is a wizard on lasers, and together with Adalberto Giussotto from Pisa University, they started VIRGO in the 80s already, and got it approved in 94. Adalberto died 2 years ago. So then I showed you that the instrument that we're using is a Michelson Interferometer, but it's a bit more complicated than that, because we use Fabry-Perot cavities to make effectively the arms longer. We use power recycling to boost with a factor 40 to 50 the power in the interferometer. So at the end, we will try to run with about 1 megawatt of power in the arms. Then we do signal recycling, and we have things are called input mode cleaners and output mode cleaners. You just clean the beam and make sure that you only get the modes in the interferometer that you want, because the rest is noise, certainly on the output. So here I have an animation that tells you a bit about how this is built up. So here you see the layout of a normal Michelson interferometer. So the reason for making the arms as equal as possible, they're not completely equal. There are reasons for that. But as equal as possible is to minimize all common mode noise that you then cancel out. So it's also important then to get the, if you later see the cavities, to get equal finesses in the cavities and things like that. So when a gravitational wave comes in from this side, and then with plus polarization, you would see something like this. One arm gets stretched, the other one becomes shorter. So what we do is place additional mirrors here. So these are the input mirrors. We call them test masses, because in our thinking, these are the free-falling test masses. and actually starting, let's say, at 10, 20 hertz, they behave like they're free falling because of the vibration isolation. And then you boost the power in these cavities. Typically, the finesse that we have is about 450. So that is about 400 bounces of the beam. Then the light is reflected here by this power recycling mirror. Here the signal is coming out here, and it's reflected by the signal recycling mirror. So you also see the input mode cleaner over there. So the way this is done with the mirrors on some support and put on the ground will never work. You need to align everything, so more than 1,000 control loops are trying to keep the interferometer aligned in angles and distances. Yeah, you saw the vibration of the ground there, so that means that you have to get rid of these supports and you need to make vibration isolation systems. I will talk more about that. So essentially these are pendula, but a pendulum only does the isolation in 3 degrees of freedom, in X, in Y, and in this angle. But you need to do it in 6 degrees of freedom. So that you need other types of vibration isolation for the vertical direction, for example. That is in here. So in all 6 degrees of freedom, these things are vibrationally isolated by typically more than 12 orders of magnitude. Depends a bit on the frequency where you are. So now if you do that, and also all your control sensors need to be isolated. The laser, the injection bench of the laser is on an isolated table. Now the ground can vibrate, but you see all the optical components are quiet. So that is the idea. So then, of course, everything has to be in vacuum. So the vacuum is almost 7,000 cubic meter. I think from the content, it's a bigger vacuum than the LHC tube. And the vacuum levels have to be better than 10⁻⁹. So we try to go in the 10⁻⁻ millibar region. And that has to do that if you have residual gas, then when the beam is going through, it's like an oscillating, a vibrating index of refraction. And that gives length differences and phase differences. So we need to have ultra-high vacuum. These towers are typically like 12 meters high, where you have the vibration isolation system. And then you stretch it. We couldn't go farther than 3 kilometers in Virgo. There were roads and canals, and it would be difficult to do it otherwise. So just to give you an impression, this is the LIGO detector in Louisiana, Livingston. So that is one is more in a swamp, and they are a bit bothered by people cutting trees and things like that. This is the most sensitive detector at the moment. It's beautifully sensitive. They go to sensitivities up to 130, 140 megaparsec. And that number is a sensitivity where you assume that you have a binary neutron star, and that neutron star comes in over the sensitivity curve from low frequencies until it merges, and you do a weighted signal over noise estimate of that. And then you average over all orientations and sky positions of that neutron star. And then you get a range. And you demand that the signal over noise that you measure should be at least 8 with that detector. So this is the most sensitive one. And here you see a mirror in this setup. So the mirror is 35 centimeters in diameter. It's about 20 centimeters thick, 42 kilograms. And these are beautiful mirrors. The coatings on that were done by Virgo. So Virgo is doing the coatings for all the facilities in the world, also for Cargara. We have huge coating facilities in Lyon. And of course, all of this now has to be vibrationally isolated. Here you see another system where this mirror is already hanging on the systems where you do vibration isolation in the vertical direction. And of course, you need to do a lot of sensing to be able to steer the mirror. Yeah, this is really a beautiful picture of the Virgo detector. Some artists thought that it would be better to paint the thing blue. I naively would have thought you paint it green so it blends in the landscape, but I'm not an artist, clearly. So it's painted blue. So what you see here is the laser is coming in from this side, and this is this input mode cleaner that I showed you. that is a triangular cavity and has a length of about 150 meters, 145 meters. That is where you clean up the beam. You do already some stabilization of frequency. Then you go into these 3 kilometer arms. And halfway, at 1.5 kilometers, we have a separate station where we have some clean rooms, etc. Here you see another picture of Virgo. So I did many experiments in particle physics, because that is where I was working. But Tuscany is a pretty nice place to do experiments, I can tell you. This is a beam splitter. So I don't know if you worked on lasers before, but typically your beam splitter is like a cube or something like that. So this is a huge 55 centimeter optics. This reddish stuff that you see there is a coating. It's a protection. So once we have installed everything and we are done, we peel off the coating and then we try to stay away from that optics. Because the power is so high, if you have any imperfections or any dust, then it will be blown up by the beam. Here you see part of the input mode cleaner. So the laser is, I don't know how much you know about optics, but if you have an optical system and then you try to inject on the optical axis. So if your laser is not injecting on the optical axis, and even if your laser has a perfect TEM 00 mode, because you're not on the optical axis in injection, you will create higher order modes in that system. Also if you are not on the right angle. So you need to filter that out. And so that is why you place things on vibration isolation system. And you can filter it out using this input mode cleaner. Now also, what we are interested in is delta L over L, the strain. That's what we want to measure. And if you use a laser to do that, then the delta L over L that you can measure is limited by delta F over F. So the relative frequency, because that is your measuring stick. So you have the frequency stabilize everything. And this filter cavity is one of the stages in the frequency stabilization. So we also stabilize our laser frequency to 1 part in 10 to the 23. So this, you need to make a triangular cavity. So this was actually made in my group. That's why I like to talk about it. And here you see 2 pieces of glass, which are almost at 90 degrees, which are welded together. And that is part of that cavity. And then 145 meters further down that tube, there is the end mirror. Here you see again that mirror. It's a 15 centimeter diameter mirror. And we had to replace it because the previous one was too light and the radiation pressure was pushing that mirror and we couldn't control the thing anymore. So now it's a more heavier one. Typically what you see here is a baffle to absorb scattered light. I don't know whether you heard about this Vanta black. That is this coating that you put on the baffles. Was the perfect black that you can get. If you want to read a very interesting story, you should look at this artist, Anish Kapoor, who has the rights on using Vanta black for his artwork. He made a nice artwork where it looked like he painted a black hole on the floor. And if you look at it, it's completely black, but it was not painted on the floor. There was a hole in there with a room below it, which he painted black. There was actually one visitor that fell into that hole. There's now a coating which is even 10 times better than Vanta black. So we use this a lot to absorb scattered light. Why is that important? If you have a little bit of scattered light, then let's take 1 ppm of power from the cavity that hits a wall. Then the wall will be acoustically excited. Now the acoustic band is from 20 hertz to 20 kilohertz, exactly the band where we are measuring gravitational waves. If that little part will come back into the cavity, then it will interfere at the amplitude level with the rest of the beam, and it will mimic gravitational waves. So we are very eager to cut out any scattered light. So this, and then you hang this on wires. And this is what they call a marionetta. It's like a puppet. Then we take this mirror and we can control it, directions, change the length of the cavities. Here you see another part. This is an optical table. And on the optical table, we have 2 photodiodes. These are just small photodiodes that are measuring the gravitational wave signal. Here you see a table which is floating. I don't know whether you can see it floating here. See that? It's moving a little bit. That is a vibrationally isolated system. So in the horizontal direction, vibrations from the ground in this table are isolated by the factor billion, and in the vertical by a factor million. And that is only because we have sensors on that table to control the beam, and we need to also keep the sensors quiet. Here you see another vibration isolation system where we put a bench on which weighs about a ton. And that is the bench inside air, where the laser beam is coming. You manipulate the laser beam, and then you shoot it into the vacuum system. So many of these things were constructed. This is an interesting device. It's called a phase camera. So what does the phase camera do? We have in the interferometer, so in the various cavities, we need to know where the mirrors are. So we need to control the position of the mirrors. You would say, okay, that is simple. If you have a cavity, you take a little bit of light out, and if the cavity is on resonance, then you will have maximum power on that photodiode, and if it goes off resonance, then the power will go down, and you have to control it back. The problem is when it goes down, what direction do you steer it, to the left or to the right? And you don't know that only by looking at the power. So the standard way to do that is that you modulate the beam. Typically, we modulate with 6 megahertz, 8 megahertz, up to 131 megahertz. And then we demodulate the signal, and that gives us the directional information for the controls. So that is, but then what you would like to do is, so in the cavities, we have the carrier light beam from the laser. It's a 1 micron laser. And then all these modulated sidebands for the controls of all these cavities. And we would like to look at them. So we are having a device that scans the wavefronts, and I can tell you the amplitude distribution of the wavefronts of all the sidebands and the carrier, and the phase distribution of these wavefronts. And that's what's called the phase camera. And you see, for example, here on the dark fringe, where you would think things is dark, you see something like, what is it, an 8-0 mode on top of that, which is probably scattering, and we try to control that. This was also part of this technology was commercialized. This essentially, what we are doing is we're taking ADCs that can go up to 500 megasamples per second, very fast ADCs. And then we do brute force demodulation using FPGAs, like the fastest Xilinx FPGAs that you can get. And some people commercialize that. They came from gravitational waves. Here you see the vacuum system. So it's a 1.2 meter diameter tube. We can send current for the tube to bake it out. And you see the containers with the isolation around it to keep the heat on the tube. We did this once, and we hope never to do this again, because it takes months to do that. At the ends of the tube, we have a so-called cryo-link. So we have 4 of them. Every arm has 2 ends. And there we try to freeze the water that we create by working in the towers. And so these are huge cryolinks, and there's enormous pumps for water vapor. And we also put vibration isolation in them, so that if the nitrogen is boiling, that you don't get this on your beam. So just to give you an impression. What I want to do right now is talk about noise, because that is the thing. When I went from LHCb into this experiment, then I think the first 10 years, all the publications were only looking at noise. The only thing we published was noise and upper limits. So noise is quite important. So here you see a schematic of the interferometer. And one of the things that is really key is that you have to get rid of seismic noise. And I'll show you how to do that. Then the gas in the tube would limit you. So 10 minus 8 millibar would not be good enough. We have to do better than that. And especially water vapor has a big electric dipole moment. That is really bad for your phase noise. Then the laser has to be stabilized both in amplitude and in frequency. There is shot noise. So you need enough power, enough light in order to be able to do the measurements. I already discussed that yesterday. But if you put in too much power, you get radiation pressure. They push your mirrors away. Then there is thermal noise, because if you just calculate kT of half kT on every degree of freedom, then you will see it is much, much larger the displacement of these atoms than what you try to measure. But since you have so many, the center of mass is displaced a little. But still, it's a limiting factor, actually the most limiting factor. Thermal refractive noise, so that the index of refraction is changing with temperature, and the temperature changes because you are putting in power. I don't know, electronic noise, that is something that you shouldn't do. You should design better. And let's go to a few of them. So one is shot noise. So the light is a stream of photons, and the number of photons is given by the power and the energy of a photon. So we have 1.064 microns. Then it's Poisson statistics. So the uncertainty on that number is the square root of n. And that gives you an uncertainty in the power that you measure on your photodiode. And if you try, so if you have a certain power in your arms, then you have this uncertainty on the power of your photodiode. But that power is also your signal for gravitational waves, so it limits what you can measure. And then you can calculate what that number is. And essentially, it's white noise with a certain RMS value, the PSD of shot noise. And the limit that you get is given by this. And I put on the typical numbers for Virgo. And you see that, you can do a better measurement if you put in more power. Now the problem is, if you put in more power, then this mirror will be hit by photons, and the static number will be dp dt, so the change of the momentum. And so this is the momentum that the photon is giving there. And also that has an uncertainty which goes with the square root of that number. So if you have more power, it's great. You get better sensitivity at high frequencies, but your mirror starts shaking, and you have this radiation pressure noise. So that is then the number at the end that you get. And this is proportional to the square root of p. So clearly what you see here is that there is a trade-off, that you can start with low power, that is 800 watts, and then you can go to 4 kilowatt or 20 kilowatt, and if you increase the power, then you get more sensitivity in this range over here. Unfortunately, things deteriorate at low frequency. And there is always a frequency where you have the optimum. And so where you could look for the optimum. I already showed you this part over here, is that where you calculate the power that you measure on your photodiode and the sensitivity to the gravitational wave, to the strain, either in phase or in strain itself. And you would naively think, okay, then let's measure here, because there indeed my derivative is largest. I have the best sensitivity in that sense. But that is not what you're interested in. What you're interested in is signal over noise. You want to optimize signal over noise. And if you optimize signal over noise and you do the calculation, you will find that you have to be here, very close to the minimum. And then also you see, yeah, but if you are close to the minimum, your derivative is 0. So you have to, again, do tricks like modulating and demodulating, and these are the things that we do. Then there is seismic noise. Seismic noise is huge, so I show you typically here in terms of acceleration, like 10⁻⁶ or 10⁻⁵ meter per second square per square root hertz. This is again amplitude spectral density. In the area where Virgo is built, it's close to the Mediterranean, so it depends a lot on the weather. So we have times that there are storms on the Mediterranean, and we almost cannot keep our interferometer locked. And things are shaking so much that we lose lots of beam time. So you can ask yourself, was that the best location to build the device? And you can answer this yourself. So what you see here is this transfer function that we talked about yesterday, and it is how would you do vibration isolation. And essentially, if you would look at higher frequencies, and you would just hang your mirror on a pendulum, then at higher frequencies, for example, starting at 10 hertz, where we want to start measuring, you already get a suppression of a factor 100 of these. But of course, that is not good enough. So you need to do better than that. And that's what we try to do. So we do the obvious, and that is cascade pendulum. Now the thing is that if you write down the Lagrangian for this, it can oscillate in many ways. The whole thing can swing like that, or they can swing like this, and there are many combinations. And that gives you all these peaks over here. The other thing is that if you want to have good sensitivity at 10 Hertz, you would like to move these peaks to as low a frequency as you can, these resonance frequencies. But now you have to calculate how long should your pendulum be if you want to have a frequency, for example, of 0.1 Hertz. And then you get something like 100 meters or something like that for a pendulum, and you see that you cannot cascade that because your tower will become too big. So you have to use smarter things. And what we typically use are inverted pendula. So things that are on the boundary of stability. And we use, so you take a pendulum like this, you put it the other way around. And then of course it wants to drop over, but you prevent that by making a flexible joint and balancing it. So these are all things that we try to do in that system, and then achieve quite a substantial vibration isolation. So that is, the pendulum is working in this direction and in that direction, and also in this degree of freedom. But you also need to do isolation in the vertical direction and the other two angles. So it's more complicated than what I'm showing you here. And then the thing is that the distance between the mirrors is 3 kilometers. And these mirrors would like to point to the center of the Earth, because that is the gravitational field. But that would be bad, because then the light would go out of the cavity. So we need to control the mirrors in a way that they stay parallel. So that gives you horizontal to vertical couplings, that gives you very stringent criteria on where to construct things, how to be close to the center of mass to avoid these couplings. And typically we can make mechanically better than 1%. And then you end up at the end with what is to be called the Virgo superattenuator. So that is the thing that if you start here at 1, and you look at the transfer function here, so it's 14, 15 orders of magnitude suppression that you achieve already at 10 Hertz. And that is what we need. And also these measurements, you can talk about it. There is no sensor that can measure that. Only the interferometer itself can do these kind of measurements. Then we use things like magnetic anti-springs. So you take magnets with the poles together so that they would like to shoot apart for the instability, and you install that to get anti-spring action to lower the frequencies. Now this device is full of sensors to do the controls. And I don't know if you ever worked with accelerometers and worked on controls, but so the idea is very simple. So you have a thing where you measure the acceleration and you want to keep it quiet, so you steer it back to that position based on that signal. But the problem with an accelerometer is that if the accelerometer is tilted, then it will measure a component of the gravitational field. Now, if you use that in your control system, you will control in the wrong direction. So you have to work that out. That is the problem that you face. So you would like to measure the tilt separately from the acceleration, and you need tilt sensors. And that is something that people have been working on for a long time. The best ones were developed in the University of Washington. That is what LIGO is using. We have been working on that at the University of Pisa, Napoli, etc. already for years. And now we have a beautiful collaboration, which came about a few months ago with CERN, because you also are measuring tilt, and that is a collaboration together with Dubna. So we are now installing that in Virgo, and to see if we can use that. And the idea is to use a liquid and to bounce a laser off a liquid, and use that to get the angular controls. Then you have Brownian motion. So the fact that you have temperature will cause oscillations, and depends a bit on the material. So the approach that we take is try to make the Q factor as good as you can. And it's based on the fluctuation dissipation theorem, is that if you have any dissipation, any Q factor, that means energy dissipation in the system, you will get fluctuations. That is already the first one that wrote the paper was Einstein in 1905 on Brownian motion. And so we try to make the Q factor as good as we can, because then, of course, here we cannot measure, because if we make the Q factor better, the peak only will become higher. But you see around the peak, it will become lower. And that is what you want. So you want to measure in the rest of the bandwidth. And so the way to do that is, for example, to take these silica mirrors and hang them on quartz wires. So that's what you see over here. So this is silica glass, 20 centimeters thick, hanging on wires which have a thickness of something like 0.4 millimeters. And they are incredibly, so I've seen the test where you take a hammer, you bang on the glass, and it stays all fine. Here you can see it again. So where you see these wires attached, bonded to the side of the mirror, and again this coating stuff is the colored part that you see there. And then it's hanging here on a marionette. And this is then hanging to filter 7. That's one of these filters, the super attenuator. We had some issues with this. We already did this in 2010. We were the first ones running an interferometer with this monolithic suspension, as we call it. Very high Q factors, up to 10 to the 8. So if you hit the mirror, then it will start oscillating. If you come back after a few months, it's still oscillating. So it's, this causes very funny things, because in the beam you can have different modes, and these modes could match to mechanical modes in the mirror, and then the beam interaction would start ringing up these modes in the mirror. These are called parametric instabilities. So it's a little energy, but it's like if you have a child on a swing and you just put in at the right moment a little bit of energy, then this swing will increase and increase. At some point you cannot do a measurement anymore. So this was observed in LIGO, and we are now using piezoelectric dampers on the mirrors to exactly at this frequency pick off the energy, so that it cannot happen. Then, again, if you have a mirror hanging on what we call a marionette, then you need to have baffles to absorb scattered light. We have a ring heater, so where we can put in power to affect the distribution of the index of refraction and tune a bit the radius of curvature. And we have compensation plates, because we have active thermal compensation. And we shine CO2 lasers on these compensation plates to counteract thermal effects on the optics. You cannot shine directly on the mirror, because that would introduce noise. So that's why we do this through compensation plates. And here you see a picture of a mirror system. So these are really nice systems with lots of developments over the year. So if you now sum it all together, then this is for advanced Virgo, the sensitivity curve that you expect. We have some of these resonances, actually many more that are now drawn where you are hanging optics from wires. Then what is limiting you at low frequency is this curve over here, so suspension thermal noise. See thermal noise in the wires. There is this gravity gradient noise, is that if the ground is having seismic motions, then you can get, for example, some additional mass, and then by the direct Newtonian interaction, it would couple. So even though you take this mirror and you perfectly isolate it from vibrations, if I would walk in the neighborhood, then I would attract the mirror to me. So also seismic density fluctuations will do that. And that is a limit. It's part of the time it will be a limit for this instrument, but for the future instruments like Einstein telescope, this is limiting the low frequencies. So if you want to measure at high Z, this is the thing that you are fighting. And then in the most sensitive part, it is this red curve over here, which is Brownian noise, and that is noise in the coatings. So the coatings that we have are limiting our sensitivity. And then over here is short noise. So this is typically the easiest part. Just put in enough power, then you can do your measurements. So we started measuring again on the 1st of April. So people in the control room are all quite relieved. This is the sensitivity that we got. We almost doubled compared to the previous run that we had. And the next one we need to double again. So this keeps going on. I don't know why we do that. So this band here is what we projected that we would get. You see at low frequencies we can do it, at high frequencies we can do it, but we have some trouble here. There is something, maybe scattered light or something else, that is limiting our sensitivity at this point. And you see this peak here, which you immediately recognize around 50 Hertz. So before this was 50 Hertz, but now we are thinking it probably has to do with maybe in the suspensions and the super attenuator or something like that. We're not convinced that this is electronics. So then you see the sensitivity around 15 megaparsec and the sensitivity of the two LIGO detectors. The efficiency of running, so this is 76% we are in science mode, so I think that is quite good. You can compare it to LIGO Hanford, LIGO Livingston, so typically above 70%. And this is when we are running as a network. Then all this part here is where you have double coincidences, and here you have triple coincidences. So if you added up our running efficiency, is about 82%. And this includes our time for maintenance and tuning and locking and everything. So that is, I think, not so bad. Since the 1st of April, so the first half year, we send out 41 open public alerts. So we used to have all these MOUs with the people in astronomy, so you can use our data, but then we have to publish together and things like that. We had 95 of these agreements, and we decided to stop with that, and we just do it open. So we send everybody an open alert. So if you want to, there is an app on your iPhone that you can get, and then you will get, in the middle of the night mostly, you will get alerts. Probably people are not doing anything then, I don't know why. And then we retracted 8 of them. Because these alerts we try to generate on a time scale of a minute, so that goes automatically. So you have to think that every detector has to run its data quality over that data. You have to transfer the data from the different instruments to the different sites, because we are running different pipelines to do analysis at these sites to try to see if we have triggers. Then we put all, for the good information, we put it together. We create sky maps. We create the probabilities that it's a binary neutron star or binary black hole and a distance. And that is what we then send out to the world. And of course, you don't want people to look in the wrong direction, so you have to do this very carefully. And we do this on a time scale of minutes, but then there is a crew that immediately starts inspecting whether this went fine. We don't trust the automation completely. And then in some cases, we retract. We agreed with the astronomers on the threshold beforehand, and that about 1 in 10 of our alerts would be noise, because they preferred not to miss anything, and they take that for granted. So indeed, it's not 10%, we retracted 8 in total. And 33, and that is what you see in red. So you can go to that site and find it, and everything in red here is then retracted. Then you can look at all of that, and so you cannot see it, and it's also not needed. You see that we make sky maps, and sometimes they are good, and sometimes they are a bit too wide. And if you summarize everything, you see these are not all the events, but you see that we have a neutron star black hole system where we find this is a candidate, and that candidate has 99% probability astrophysically that this is a neutron star black hole. We have a BNS candidate with 99% probability that indeed this is a binary neutron star, and then some mixed probabilities on other systems. The rest are all binary black holes. This is an interesting one because this is the distance up to redshift maybe of 1.6. So that is almost 7 gigaparsec. It's an enormous distance. And we are analyzing all of that. We have dedicated teams on the things that we believe are most exciting. And of course, it would have been great if the astronomers would have found the counterparts. But they have difficulty doing that right now. All of this is based on transients. And our data analysis is more than that. So we do this coalescence of compact sources. But we also have a group that is looking at continuous wave, deformations of, for example, neutron stars, little mountain of a neutron star, and because it's spinning, it constantly is emitting at a certain frequency these gravitational waves, and we try to filter that from the data. So while these transients are typically short, often less than a second, these signals will be there all the time. So we integrate them over months. And we try sometimes to log in to the optical, the RF signals that you have from pulsars. So far we didn't find it, but the sensitivities that you get in this manner are much, much more precise. And since the Earth is rotating, if you would find a source, the pointing would be very accurate. And also, since your antenna pattern is then constantly changing, you would really be able to find all the polarization components. So we're doing that, but not successful right now. Our data is open, so maybe you can find it yourself, would be great. Then we have a burst group that is looking, for example, for supernovae, but they also do the analysis of these events and treat them as a burst. And then there is the stochastic analysis group that is trying to look for stochastic signals, maybe from the early universe. So the continuous wave group is mostly looking at neutron stars. These are probably too many details of what they're looking at. Here you see the Crop pulsar. So the Crop pulsar is a neutron star. It's about 900 years ago that was created. And we have the RF signal of it, and we're looking for gravitational waves in that system. And we know that of the energy that is emitted, less than 1% is emitted in gravitational waves. But what the real level will be, we don't know. And there are many, many models that tell you that we, at some point, should see something. Many publications, so I leave that in the slide. If you are interested, you can look at that. And we're also looking at stochastic. Now, one of the issues that we get here, of course, it's great to find signals from the early universe, but what we certainly are going to get are a stochastic background from the black holes. And all the black holes at a subthreshold that we don't measure right now, they will make some stochastic noise. And I think there is a good chance, this is all free, that we already could maybe start probing that stochastic noise. If we don't succeed in this run, I will be disappointed if we don't succeed in the next run. I think then we really should find it. So that will then be a background for the other signals that we have to subtract. And then, of course, all these surprises. So there are numerous publications on that where you see our sensitivity band and somebody predicts that in the center of our sensitivity there will be a beautiful signal from a phase transition. We will see. Okay, so a little bit down the line. So this was LIGO+VIRGO. So what is operational right now are these detectors. And Kagura is the next one that will come online. We want to have more detectors because now our pointing accuracy is typically like this. So at some places we don't have any sensitivity, some places it's quite bad, and at some spots in the antenna pattern the pointing is good. So this will be in the next runs, and this is if you have both India and Kagura joining. So then you get significantly good pointing accuracy, and this is what you need for multi-messenger astronomy. So this is the Kagura detector, and so all of you know about Super Kamiokande. It's in the same mountain. There is an overburden of about 1 kilometer, so everything is constructed. So it's there, the interferometer is locked. And so I was there last week. So Kagura is the name also has to do with some music and some philosophy. So there was a performance of these students doing a Kagura. And then we had to sign the agreement. So we always talked about the LIGO+VIRGO collaboration. Now we should talk about the LIGO+VIRGO-Kagura collaboration. So they're part of the collaboration, and we hope that this year they would join with their detector, and then we even can do more science. So here you get another impression with the light on. So you see it's in a tunnel, and So the length of the arms is 3 kilometers, like Virgo. This is LIGO India. So LIGO India was approved by the Indian government on the day that we announced our discovery. So that was good. And now all the land has been acquired. There is a collaboration between NSF and the Indian government. So NSF will provide lots of equipment. So they acquired the ground right now. Construction is started. So you see these poles are now there with LIGO. And the hope is that maybe 2024, 25, it will be operational. So then what is next? Now, is that LIGO and Virgo would like to improve their sensitivity. So we, of course, are limited by the constraints of the site. We cannot go from 3 to 10 kilometers or put it underground. But certainly we can improve things. And the reason for that is that we just made a discovery a few years ago, and we are completely limited by sensitivity. So if you would have all the sensitivity in the world, then typically in the universe, every few minutes, there is a collision of binary black holes or other things. So if we only measure 1 a week, then clearly we're limited by sensitivity. So we want to improve that. And the thing is, both LIGO and Virgo, you always have to do things in a synchronous way, otherwise scientifically you become irrelevant. And both of us are upgrading. So after we're preparing right now our upgrade, and as soon as we are done with running in April next year, we'll start installing and commissioning. Because when we can improve the sensitivity by a factor of 2, then in the next run we will count a factor of 8 more events. Because it's a volume that you're probing in the universe. So what we want to do, we do it in 2 phases. So the first phase is that we try to improve our sensitivity and get close to the limit given by thermal noise. And that means especially that at these high frequencies, you want to put in signal recycling. That is something that we need to do. And also we do squeezing. And I will say a bit more about that in a second. So that is the first step, and that should bring us from the 50 that we have right now to more than 100, maybe up to 150 megaparsec. Then the second phase is trying to push this thermal noise limit down. That means changing your test masses, making them bigger. We think about more than 100 kilograms for the end mirrors, putting on better coatings. And then we could get another factor here, maybe up to something like 250 megaparsec if we achieve that. So that is the goal of this upgrade. And there's a similar upgrade at the LIGO side, but LIGO will not change the size of the mirrors. So they will put in new coatings. We are working together on the development of that. So if you look at these mirrors and coatings, then everything is made by LMA in Lyon. If you read in physics books about a perfect mirror, this is the closest you can get to a perfect mirror. Okay? So if you would take that mirror and you would amplify it to the size of a city, let's say take Paris, that would be your mirror, then the flatness of that mirror would be the width of a human hair. So it's completely flat. The biggest mountain would be like 5 atoms high. So that is the technology. Then we put on coatings, like 15 layers of silica and tantalum, and stack it to get perfect absorbing, or perfect mirrors. So with only very, very little absorption. And still, the noise in that coating is limiting our sensitivity in the most sensitive part of the interferometer. So if anybody can find a better coating, be my guest. So let's see. So the other thing is squeezing. So squeeze the vacuum. That is another big thing. We're already using that right now in both in LIGO and Virgo. We installed that for this run. That if you have the mirrors and you measure the position very precise, the delta L, then according to the uncertainty principle, you don't know the momentum. So that means after that measurement, you don't know, you have an uncertainty on your momentum. That means that if you measure a second later, that you don't know where your mirror is. You have an uncertainty in that. So that is your quantum limit. So now what you can do is you can manipulate that by injecting so-called squeezed light. It's like noise that you inject through the dark mode of the interferometer. And what this achieves is that you don't care if you want to measure this length. You don't care if the uncertainty is in this degree of freedom or that degree of freedom. So you try to manipulate the uncertainty in different regions and different degrees of freedom where you don't have your sensitivity. So that's essentially what you're doing here with squeezing. And of course you can say, yeah, but I have Poisson statistics, so how can that be? Now, in reality, what you start doing is you start using correlated photons. And you build in the correlations in the noise that you inject. And that is how you can do better. So here you have, typically if you don't inject any of that squeezed light, which is a very small amount of light, but if you inject it with the right phase, then indeed you become more sensitive here. But if you inject it with the wrong phase, it becomes bad. So you have to do it right. And what you see here is that at low frequencies, it goes in the opposite direction. It's difficult to see right now, but if you squeeze, then it turns out you make things worse at low frequency. So that is why we need to do frequency-dependent squeezing. And that means we have to build another 300-meter long cavity to start rotating that squeezing angle. And so people are working on that. And we will install that starting in April next year. Then I talked about this Newtonian noise, these fluctuation densities that couple directly to the mirror. And so typically background electromagnetically you can shield by making Faraday cages. You cannot do that with gravity because you have only one charge in gravity. There's only one sign. So what you can do is try to put many seismic sensors and measure the fluctuating field and try to do a subtraction of it. So make Wiener filters. So we're doing that too. And this is then the goal. So, but I already told you, we synchronize this completely with LIGO. So we run until the end of April next year, then 20 months we'll do the installation, then we run for another year with an improved setup, and after that we do the remainder of the upgrade. So this is not it. So this is what you can do with LIGO and Virgo and Kaga and LIGO India, but we are dreaming about the third generation, because all of this before is so-called second generation. So this is the next generation. And there you want to get another factor of 10 sensitivity on the design sensitivity, which we didn't achieve yet for LIGO and Virgo. And there are two ideas there. One is Einstein telescope. So there are two sites for that. This background is actually where I was born. I was born like 20 kilometers from there. That is nothing to do with the choice of the site, of course. But this is the border region between the Netherlands, Belgium, and Germany. And there is another site, which is Sardinia. That is what other people in this collaboration would like to do. So we have two sites that we are investigating. And then there is a plan in the US to build something that's called Cosmic Explorer, where right now they're thinking about arms of 40 kilometers, while this here are arms of in the order of 10 kilometers, but in the form of a triangle. Here are 6 interferometers installed in that same triangle. If you look at the sensitivity and the range that you have, then on masses, you can go to from a solar mass to something of 10,000 solar masses. So you can look at intermediate mass black holes. Then if you look at the redshift that you can reach, it is up to a redshift of 100. So to put this in context, if you look at the beautiful pictures that Hubble has made, the farthest that Hubble ever could look in the infrared was a redshift of 12. And maybe with the James Webb telescope, you can go to a redshift of 20. We are talking about 100. So essentially, if you do that, then what you can reach are the so-called dark ages here. So you call that dark ages because that is before the formation of the first stars. So then you can say, yeah, but why do you want to look there? There were no stars, there would not be any black holes. Yeah, that I probably might disagree with you because you know that already at redshifts of 7, you see black holes of billions of solar masses. And they had to be generated from something. And if you look at the models for black hole generation, and you start here at a redshift of 40, and so you come then to today, which is redshift 0, you see the formation of all these black holes and the building up of black holes. So while there may be no stars, it might be a very wild and exciting region for black hole collisions. And Einstein telescope will be the instrument to look at that and try to figure that early universe out. So that is the motivation. So we are trying to put this together. And essentially, right now, we need the support of everybody. We need to make a European proposal. We want to be on the S3 roadmap, so we will submit a proposal next year. Then hopefully in 2021, we will be on the roadmap. 2022, we can make a site selection. And then hopefully in the 30s, we would have an instrument. So with that instrument, you would see all the events in the universe. You would see all the collisions with good signal over noise. So you can do cosmography with that, use them as standard candles. The events that we're seeing right now, you would find them at a signal over noise, some of them of 1,000. So they will be lines. You would get at all these post-Newtonian parameters, etc., that I discussed yesterday at the sub-per-mil level. So you could do very, very precise tests of theories of gravity. Right now, our numerical relativity is limited to a signal of noise of 100. So that means there's a lot of work to do for theorists if you really want to use this and test general relativity. So if you think that these supermassive black holes are built up in a kind of hierarchy, then you should find intermediate mass black holes. So we will look for that. So all of that determines that you need to have a very good sensitivity at low frequencies, because the signals that you measure will be redshifted to low frequency. So that merger that I showed you, the first detection, that merged at 150 hertz, if that would be at a redshift of 10, it would be at 15 hertz. A redshift of 100 would be at 1.5 hertz. So you need to have good low frequency sensitivity. Then if you want to have all of these precession effects due to non-aligned spins on the amplitude and on the frequencies, then you need also low frequencies to measure long waveforms. Then, I think a supernova right now will be the event of a century, so I get carried away if I talk about that. Pulsars, we could see mountains of pulsars of a fraction of a millimeter. So that is something that you could pick up with third generation experiments. And then hopefully you would like to see the things that nobody expects, that nobody thought about. So that possibility is that you have. You will collect over a few years a data sample of millions of events that you can cross-correlate with the information that you get from other experiments like SKA with radio. Also LSST will build up huge data sets, and Theseus in X-ray, for example. So the cross-correlation might also give you lots of information on cosmology. So this is the device. So 10-kilometer arms, a few hundred meters under the ground to get away from seismic. I have this, I couldn't resist to do that since I'm here. And I think there are some parallels that you can draw with CERN. First of all, the scale. So this is the LHC, 26 kilometers, and this is 30, this is ET, so that is similar. They're both underground, they're both ultra-high vacuum systems, they have lots of control, cryogenics, it's all there. This is the FCC, so compared to the FCC, this is like, you know, it's a 10% perturbation or so. I think scientifically, from the point of view of science, I think there is like elementary particles, also space-time are building blocks of the universe. And so intellectually, I don't see a big difference. If I look, the Virgo collaboration has almost grown by a factor of 2 in the last 2.5 years. Most of the groups came from particle physics, be it from Atlas, CMS, Alice, LHCb, and they got attracted to also work on this. I think what we also could profit from, so apart from all the technical knowledge here, is how to handle such a big project, because for us this would be difficult. How much time do we have? Nothing. Okay, so I had the last 5 minutes on gravitational waves in space, so unfortunately I will skip that. Go away. And this is my last slide. Okay, so thank you. I leave it at this.
Okay, great. Thanks so much. This was really a great lecture. So the speaker will have to leave relatively soon, but we have time for a few quick questions. Try and go quickly.
Sorry. Concerning the sensitivity that you mentioned, so you have 10 to the minus 23, right,
right
in advanced LIGO. If I'm interested in correlation measurements between LIGO and Virgo, assuming that I'm always, say, below 100 hertz for correlation. Yeah. So the question is, in omega GW, you showed the plot, and you said that you go to 10 to the minus 9. This means on the correlation, not on the single detector, right?
So say that again, that last sentence.
So it's on the correlation.
What is the 10 minus 9?
Omega GW that you showed in your plot for the stochastic, for the correlation measurements, goes to the minus 9. Now, this is on the correlation, not on the single detector.
Yeah, that is on the correlation. But the problem that you have there is that depending on the frequency, Virgo might be a bit too far away from LIGO. Okay, and so you might better do it.
For the two LIGO, it is on the correlation, meaning integration time of 1 year or so.
Yeah, yeah. Okay. And so I think it's better for that part to maybe stick with the two detectors that are closer.
Yeah, yeah. For 1 year of correlation.
Yeah, yeah.
So for the Einstein telescope, you showed that you want to have a 10 times higher sensitivity, but then at the same time you say that for LIGO and Virgo, the limiting factor in the most sensitive region is sort of the coating and the Brownian motion in the coating. Is there a path forward for that?
Yeah.
Or is this like a bottleneck that isn't solved yet and that you don't know how to do it yet?
No. I think we have, I think the plan is reasonably solid that what we want to do. So the difficulty is to achieve good sensitivity over the entire frequency range in one instrument. So what we decided for Einstein telescope is to make life a little bit simpler and use what we call a xylophone. So we have one instrument that is optimized for the low frequency and one for the high frequency. That if you look at the sensitivity curve of Einstein telescope, you see this funny wiggle in there. That is because there you match and the total sensitivity curve. So the high frequency, you are short noise limited, you put as much power in that interferometer that you want, but that would destroy your measurements at low frequency. So in the low frequency interferometer, you use little power. So that is one thing. Then what you do is you use test masses, which are very heavy, hundreds of kilograms, to make sure that the radiation pressure has difficulty displacing these test masses. You try to make bigger beams, because the bigger beams would average more on the noise of the coating. And you try to get better coatings. And so there is that in total will help you. Yeah. And also I think that is the reason to go underground.
Talking about the noise of the coating, I thought to remember that you said something that the noise of the coating was mostly thermal noise.
Yeah.
Do you intend to cool them?
Yeah, that is what in Japan, the detector is using sapphire, and that is cooled to 20 Kelvin. So indeed for these noise effects. So the low frequency interferometer, we have these big test masses and we want to cool them to also something like 10, 20 Kelvin. And if you look at the coating, so then you need these quarter wave length layers, lambda over 4, and you need to stack them with low and high index of refraction alternating, and not too many. So it is especially in the high index of refraction layer, that is the Tantala. And there what we discovered, if you sprinkle a bit of titanium in that crystal structure, your noise goes down. Now, so we are investigating now to do better than that, and maybe use crystalline coatings or other approaches. But that is, yeah, for me, a very difficult field to judge. And probably I'm not the only one, because we didn't make a lot of progress on that in the last 10 years. But we'll see. So that is just limiting us. I cannot say more about it.
And then what about radiation cooling? I mean, if you have a black cold surface
yeah.
next to the mirror, and the mirror has a black, and the rim, black surface, I mean, could you cool it by radiation?
No, that is what we do. Want, the thing is, if you have these big optics and you need to cool them, then you cannot touch them. So because then you would introduce noise. And then you can hope that through these thin wires you get some cooling, but most of the cooling is done through radiation cooling. And of course, what we do is we make things like contact gas when we cool it down. But a cycle of cooling down the mirrors to a low temperature and heating them up in Kagera in Japan takes about 3 months. So you better think in advance about all the things that you want to do, because the time constants are very long.
This is also true for the LHC.
Yeah.
More questions?
For the cosmological aspect, means measurements at high redshift, how does the ground-based approach compare with the space one? Because one probably assumes that the sensitivity in space is towards lower frequencies. Or
No. I think there are plans. So the plan in space right now is LISA. So LISA is approved, launch date of 2034, and that will go and do the measurements. But the arm length is 2.5 million kilometers for LISA. So now, if you would like to be optimal for the cosmology that we are talking about right now, you would like to have sensitivity around 1 hertz to maybe 10⁻⁻1, 10⁻²hertz. So your arm length should be shorter. So there are plans for that. There is a project in China that are contemplating to do a space mission just for that. There is an idea in Japan. It's called a Cosmic Explorer, where you would have, but these are very, very expensive and will take a long time to develop. But they might, at the end, be simpler than fighting this seismic noise here, because you don't have the seismic noise, and if you have longer arms, what you're limited by shot noise, and shot noise is just laser power. So that might be simpler, but it is for me difficult to talk about LISA and these kind of space missions and then call them simpler. But
okay, so we have to wrap it up there. So let's thank the speaker one more time. Maybe you can email me when you land or so, because
yeah.
I'll do that.
Thanks so much. This was great.
Sure. Okay.